Hi, today we're going to be doing the graphs of exponentials and logarithmic functions. So first off, you have to know a keyword called asymptote. And an asymptote basically is an imaginary line that a curve will approach but never intersect it on a graph. Okay, so we are going to sketch a basic exponential graph, y equals 2 to the x power. So as always, our graphs, we are going to go to our y equals, type it in, and first we'll look at the graph. Okay, so I will put that picture down here for a second. So when we graph, we want to go to the table and graph some points. Now you really also want to get this section of the graph, so don't just stick with the positive values for x. We're going to go back also and maybe go back to -3. You should write the table on your paper. You don't get points off, but it is a really good idea to do this. Okay, so -3 is about 0.125. That's just really above the x-axis. It's really hard with my big markers to do this. Okay, you'll have an easier time than me. Okay, so that's what the graph will look like. And then we connect the dots. Now it's definitely going to go up and continue in that pattern, and it's also going to come down. And then it's going to just skim that x-axis. And the reason is because you have y as an output. Now, y as an output means that every 2 base that we raise to a power gives us our y value. We will never, ever, ever, ever be able to raise 2 to a number up here to make it equal 0. That'll never happen. So that's why it'll never hit 0. And there's also no power in the world that I can make this become like a -2. You can't raise a base to a power and also get out a negative value. That will also never happen. So that's why the graph will just go along, but not ever hit the x-axis. So it's going to kind of dip down toward it and never reach this x-axis. So we use a dotted line to show that there's an imaginary boundary there, and that's what our asymptote is. And it's the x-axis, which actually is the equation y equals 0. So the graph will continue to go down closer and closer, but never reach that. Now, there's also a few pointers that you need to know. And I have them in the gray box. The first thing is the point 0, 1 will always be on a basic exponential graph. And this should make sense. Again, let me write the equation. If I plug in a 0 for x, then you will always get out a 1 for y, because a 0 power means that it's going to have a 1 value. So this point right here is always on a basic exponential graph. Number 2, we talked about a basic exponential graph has an asymptote at y equals 0. It'll never touch that x-axis because you can't ever get a value out of 0 or negative. The domain is going to be all real numbers because there is no limit on what x I can use as an exponent. So any x number for an exponent will be fine. And the range, I will never, ever, ever get down here. So this is not going to be in the range. It's going to be only the numbers for y that are above 0. So therefore, the range is all the y's greater than 0. Okay, so for number 2 now, we are now going to sketch below the graph of y equals log base 2 to the x. Okay, so this is what our final graph is going to look like, and I'm going to go to the table to get some points. So those errors mean that those are not even going to happen. We cannot ever plug in, for this particular problem, those x numbers. So we are going to definitely start at 1, 0. Now remember what this means. Log base 2 means what's the exponent that makes 2 become a 1? Well, the exponent is 0. What exponent makes 2 become a 2? Well, the exponent is 1. What's the exponent that makes 2 become a 3? Well, that's not pretty. That's why you get that ugly number. And then when you get to 4, what's the exponent that makes 2 become a 4? It's 2. You can also skip around. For instance, maybe we'll go to the next table. So you don't have to graph a function right in order by the table. So we can go ahead and go right to our next number. We can even eliminate that. We can go to 8 is 3. And hopefully you realize that that's 2 to the third is 8. So 2 to the fourth, the next good number is not until 16. Okay, so 1 is 0. 2 is 1. 3, I don't want to graph 3, so we're going to go to 4 is 2. And then 8 is 3. I'm over 1. And then there's our graph. Now, I really need to show what's happening down here in this section right there. So I am going to go now back to my table. I'm going to go to Table Setup, second window, or on the Inspire, when you're on your table, hit Menu and Table Settings. I'm going to have my table start at 0 and then go by maybe 0.1s so I can see what's happening in between. So maybe I want to graph the 0.5 number and the -1. Again, your table can be out of order, so it's okay if we do that. Okay, so that'll at least give me my graph to go down. Again, just like an exponential, it's going to follow some imaginary line. It will never cross the y-axis. That is the line x equals 0. That's the asymptote. And we talked about this when you do solving. You can never raise a number 2 to be anything other than a positive number. That's why remember, that spot there means it's the outcome. So that outcome always has to be positive. So x has to be a positive value for that spot with logs. So going to our gray box, we have a couple also neat things. The 0.10 will always be on a regular graph of a basic log, because that means that, and if I write that in there, log base 2, the x value is 1 is 0. That means that if you have a 2 base and you raise it to a 0 power, you always get 1. So 1, 0 will always be on a basic graph. The asymptote we talked about, it's never going to cross that imaginary x equals 0 line for a basic log graph. The domain are all the x's bigger than 0, because as we said, the outcome of a log base 2 can only be positive. So that spot here has to be positive. And then lastly, the range, you can have any x or y exponent. Remember, now the y is the exponent. So you can have any number, so you can have any y number come out. Your range is all real numbers. Now, I'm just going to do this. You don't have to do this. I am going to put the, actually, I will do it on the other page for a second. No, I'm going to do it here. I'm sorry. I'm going to just put the original first problem's graph on this graph. So I'm going to put the y equals to the x graph right here. I don't want you to do it, just I want to show you this. The y equals to the x graph is going to look like this. So this is y equals to the x. There's a special relationship. Remember I told you that exponentials and logs are opposites, like inverse functions of each other. This is an inverse function. Inverse functions are reflections over the line y equals x. So if I put the line y equals x here, you're going to see that relationship. The table for these are reversed. Remember, inverse, you switch x and y. So this is what's going to happen is you're going to switch x and y to get the other graph. That's another way to graph a log, is to graph the original 2 base exponential and then switch the x and y log for log. Okay, next question. So again, that was just a side note. We're going to be doing inverses in a second. I wanted to show you graphically what was happening. Okay, so next problem. Which of the following numbers is not in the domain? Well, if it's in the domain, in this spot right there, this spot has to be positive. And again, we talked about this when we did solving. So as long as it's positive, it can be in the domain. If it's 0 or negative, it's bad. So on this particular problem, -7 would have been our reject. All the other ones would be fine. You can't have a negative value there. So problem number 4, what number is not in the domain? So again, anything after the log, that piece needs to be positive. So you can do one of two things. You can either substitute the numbers in. For instance, check 0. 5 minus 0 is 5. That's positive. That'll work. You can keep on going with the rest. Or you can set up this equation. I know that the 5 minus x needs to be positive. That means more than 0. So I can go ahead and then solve this if I really want to. Okay, so any number that's less than 5 is going to work. Any number 5 or more is not going to work. So basically, that means 5 is not going to work. And when you substitute 5, take away 5, you will get 0. And you can't have a 0. It has to be positive, so above 0. Okay, and the other thing you have to know how to do besides graphing exponentials, graphing logs, knowing those important key facts I have in the gray box, you have to know domain, that spot needs to be positive after the log. The only other thing you have to do is know about inverses. And we already talked about how inverses of an exponential are log. So example 5, write the equation for the inverse of y equals 6 to the x. Well, we know for inverse functions, you switch x and y. Okay, so if I want to find the inverse of y equals 6 to the x, I'm going to switch a y to an x and an x to a y. And as always, we get it back in y equals form. And in order to get to y equals form, we do this when we do solving. I need to bring this y down. And in order to bring a y down, it's going to involve switching forms. So I'll start off with the log. Log, the base is 6, the outcome is x, equals the exponent y. And then there's your answer. Okay, we can also go backwards. What's the inverse function? So again, we're going to switch x and y. And then again, I need to get in y equals form, so that's going to be switch forms. All right, 9 is the base, x is the exponent, equals y is the outcome. So some of the things you have to know about these that I've already discussed. The graphs of the logarithmic and the exponentials. So exponentials and logarithmic graphs, they're a reflection of each other in the line y equals x, which means that if you have a point on one, the reverse is on the other one. Okay, and that's pretty much it. Now you can try to do some practice problems if you like and check your answers.